Hello, my name is Bob Tipton, and this is a presentation by Dark Sky Innovative Solutions on our OroAzul project and the part on deep ocean energy. It's part of OroAzul's systemic roadmap for turning fossil fuels into the fossils they deserve to be and achieving global sustainability. In this video, we start assembling the pieces. In videos 1 and 2, we showed how to use low-cost, ultra-simple collectors to generate virtually free energy from the oceans. We've had a presentation on using large-scale ships, such as container vessel-sized ships, and we did a section on using smaller dispersed units for indigenous power generation. In Video 3, we showed how to store that energy as highly compressed hydrogen underwater. That was a bit sciencey and mathematical. It had to do with engine cycles and compression. And in this video, we are going to apply that to redeeming sea monsters, these giant prolific drilling rigs that we have thousands, tens of thousands scattered around the Earth's oceans. Governments are trying to figure out what to do with them, how to tear them down, who's going to pay for it, and what to do with them. Oil rigs as amusement parks. This operating amusement park in Saudi Arabia is one way to repurpose one rig. We're looking at a better way. But I'm leaving this in the scene. If you look at this, we have 3 water parks, we've got a helipad, we've got a cruise liner coming in, we've got tour boats, we got water, we have a Ferris wheel. These things are huge. There's a roller coaster over here. These things are immense. So, we're looking at stealing from the opposition. Well, possibly with their cooperation, but we need their stuff. We not only need their physical platforms, we're also planning to hijack their technology. Due to humanity's quest for oil, it's now possible to do ocean operations at 3,000 meters depth or more. This chart shows the progression over time of human desperation seeking oil, where we keep going deeper and deeper and deeper. We went through the 2-kilometer mark around 2007. We hit the 3,000 kilometer mark around 2010. And if I remember correctly, Deepwater Horizon is in around 4,000 feet, which is the bottom of the abyssal plain of the Gulf of Mexico, which is pretty much as deep as the oceans get. So thanks to Halliburton and Schlumberger and the oil companies, we can now tether and moor structures pretty much anywhere in the Earth's oceans except the deep oceanic trenches. So, let's look at OroAzul applied on oil rigs. Remember, OroAzul is basically a concept. It's a fundamental concept of an ocean-type piston where you close a collector, the current pulls the collector at very high force over a very long stroke. At the end of the stroke, which is coming up, and here it's under a 90-meter vessel like a container ship or small oil tanker, as it gets out the end of the stroke, it opens, the force drops, we reel the thing back in to start, we close it up again, the stroke resumes. It's a very, very powerful stroke over a very long run. Deep ocean operations, you can expect a run of this sort between 0.5 kilometer and 2 kilometers long on these cables. And these cables generate a lot of force. That force drives a generator. Now we get into the mathematics, because one of the big questions on this is scalability. There's a widespread belief that quote-unquote drag machines are not scalable. But that appears to apply only to rotary drag machines. Linear machines, where everything is in tension, appear to be quite scalable. So let's look at the numbers to back up my claim. This is all based on Bernoulli's equation, which is 1/2 rho v squared for the dynamic pressure of a fluid. So when we apply that to power, we come up with a formula of 4/27 1/2 rho CdA v cubed. The 4/27 comes from the optimal power curve, which shows that you extract maximum power from a moving fluid when your collector is moving at 1/3 the speed of the fluid. When you factor all that out, you come up with a number of 4/27. 1/2 rho is the density of, in this case, seawater, which is 1,027 kilograms per cubic meter. CD is the coefficient of drag. That's a shaping factor. High drag is a high number, low drag is a low number. we're using, I believe, 1.6 in these figures. We can go as high as 2.3 to 2.5 with our new high drag sail designs. A is the frontal area of the collector, and V is the V squared for force times the V for velocity to get power. Force is equal to 1/2 rho CdA 2/3 V squared. Because it's 2/3, because for optimal power collection, the collector moves at 1/3 of the current velocity. Now you can move at a different speed, but you'll be slightly less efficient, and thankfully it's a pretty flat curve. You can go from like 1/6 to maybe 5/8 and still get like 80-90% collection. So we have some room to play with on these velocities. All right. The span we're looking at is 40 meters across. That's from the base of one of these leaves that's just opening right now to the tip. There are 2 leaves per collector. That comes up, this design, to be 1,250 square meters. We're estimating with a velocity of 4 knots, and we come up with a power of 14 megawatts off this one collector, of which we see 6 in the video running in the background. Now, if you want to scale this up or down, if you double the speed, you get 8 times the power and 4 times the force. And if you get half the speed, you divide by 8 and divide by 4. But the thing that really drives scalability is the force. When does this stuff break? When do you have so much force that the whole system, falls apart? And the force here is big. It's 10,500,000 newtons. That's 1,180 tons in the US English system. So we're talking big ocean power, oil rigs way out in deep water, big heavy stuff such as the oil companies use. But we're going to try to use it to save the planet and redeem the oil drilling instead of what they did. We're going to try to clean up their mess. So we're going to be into ocean scale thinking to do this. So we have done this before. Humanity has built gargantuan moving structures in the past. The most well-known and oldest is the Panama Canal, and here we're looking at the Gatun locks. That's a big container ship going through there. The world's container ships are limited by the size of these locks because we built these over 100 years ago, and no one wants to go back and build them again. So this is what we've got. On the lower left is a relatively new construction, which are this is a Falkirk wheel in Scotland. The Falkirk wheel solves a problem of how do you move a canal boat from a lower canal to an upper canal or down to the bottom. So if you look carefully in the photo, you'll see what appears to be a city bus. That is a city bus on a barge or a city bus-sized canal boat. And if you look carefully in the other pocket, on the other side, there's another one. That's 2 city buses. And to make it even heavier, they are both floating in the canal water. And this gargantuan machine actually picks up a city bus and its water and a couple other boats and lifts it up about 100 meters up here and then lowers it back down. I don't know, maybe it's only 50, 75 meters, I'm not sure. But it's lifting these huge weights, these high altitudes, driven by an electric motor. And on the lower right, we have the Pont Jacques Chaban-Delmas lift bridge in France. And that center span that we see lifted up in the air is 110 meters across. That is larger than a football field and made of ferro concrete, and they lift it up and down 2 or 3 times a day to let the boats go through while they interrupt traffic. So, one of the things people don't realize is that every electric motor can be used as a generator with the proper wiring, and every electric generator can be used as a motor, again, with proper wiring. A motor is a bad generator, a generator is a bad motor, but they are fundamentally the same device with slightly different tuning. So if we can use motors to lift these huge structures, we can build large, slow generators. So large, slow generators are definitely doable. But still, 10,500,000 newtons is a lot of force. Like I said, it's over 1,000 tons. So enter Spectra cable. Just for comparison, the force on the Gatun lock doors is 24 million newtons. And that's done as a pivot on a door. So they're doing 24 million newtons on a swinging door. That's worst case if the one side of the door is empty and the other side of the door is full. At the depth of the locks, you're looking at about 24 million newtons on a pivoting door. Well, Spectra, some of you may know, is it's advertised as the rope that floats. It's similar to nylon. It's a synthetic rope commonly used. Hikers and climbers use it all the time, sort of people in boats. But it is made in industrial sizes up to 4 inches in diameter with a strength up to 4 million newtons. So we have 10 million newtons, 4 million newtons per cable. If we use 3 cables, 3 by 4 is 12, we get 12 million newtons of force from 3 off-the-shelf Spectra cables, and I'm sure the people who make Spectra will be more than happy to run a kilometer-long length cable and charge us money for it. So we can handle these loads with off-the-shelf equipment. So what we're looking at is 10 times the power of U.S. current wind off of existing oil rigs, both derelict and active. The U.S. generating capacity is 470 gigawatts, and there's an asterisk up there. I'll get to that in a moment. We worked out that we get 14 megawatts per collector in that image. U.S. data shows there are roughly 1,500 rigs in U.S. waters. If we put 20 units per rig on there, and of course we're going to cycle them like an auto engine so we don't have all the force hitting at once, and we will undoubtedly have to put in more supporting cables to keep these things getting towed out of position. But we come up with 443 gigawatts, and we can move that around. We can change the size of the collectors, we can change the size of the generators. This is just a rough guess. Okay, well, let's look at what we have now. The US EIA, the Energy Information Administration, says that current U.S. electrical generation in 2021 was 412 trillion kilowatt hours. Note, kilowatt hours, not kilowatts. If you divide by the number of hours in a year, you get 470 gigawatts, which is the figure we had up above. But there's still an asterisk on that, which will go down to the lower right. Other EIA figures show that we actually have electrical generation of 1,100 gigawatts. So somewhere in here, either I was totally confused by their presentation and I'm mixing apples and oranges again, or there is a disconnect in the EIA data. One of the two. We'll get to that in a moment. So basically, we're looking at what this chart has published for U.S. consumption. Of that electrical generation, 20% is renewables, all renewables, including the hydro dams. 20% roughly is nuclear, and the remaining 60% is fossil fuels. So if we take 9.2% of 470 gigawatts, we get 43.2 gigawatts for wind. We do the same for solar. We get 13.2 gigawatts for solar. They add up to, what are we at here? 9 and 3, 12% total capacity, of total generating capacity. But OroAzul, if we put it on the oil rigs, racks in at 443 gigawatts, which is slightly more than 10 times the entire contribution of U.S. wind. If we did all of OroAzul, add these numbers, we would be over 100% of what's listed as U.S. electrical generating capacity, unless this 1,100 figure is accurate, in which case we would put more of them out there. Way to go. We have ended. We have solved the U.S. electrical generating problem. Yay! Set up the bands. Let's all go have a party. Sorry, folks. Not enough. Hate to spoil the party. Okay. U.S. total consumption is 100 quads. A quad is 1 quadrillion BTUs. Don't ask me what a BTU is just yet. If you go through the math, punch it into an online unit converter, that comes up to be 29,307,000 gigawatt hours. If you divide by the number of hours in a year, you come up with a total U.S. power consumption of 3,340 gigawatts. If you divide the 470 from the previous slide by the 3,340 from this slide, it shows that electrical is only 14% of total U.S. consumption. Total U.S. consumption. So if we did this to all the oil rigs, the whole shebang, we would still have 6/7 of the fossil fuel demand still out there. We have only done a drop in the bucket. Renewables plus OroAzul can supply all the electrical, but we've still only handled 14% of consumption. I'm going to take a brief moment here. I had to redo this presentation several times, and I had to redo it because of this presentation from the EIA. Trillion kilowatt hours. I have to do math to interpret their chart. And every time you ask anyone to do math, even a mathematician or an engineer, there is a chance we get that math wrong. We then go through all the plethora of units. So we are in unit and data carnival. The physics is easy. Slogging through the units and data is 3-card Monte. We all know 3-card Monte. Shuffle card here, shuffle card there. Which one's the card you picked? Okay? So in the metric system, we have kilogram, newton, joule, watt, and kilowatt hour. Kilowatt hour is just combining metric time into metric energy. And I tend to gravitate toward kilowatt hour because almost everyone on the planet pays their electric bill with kilowatt hours, probably the most commonly known metric unit after the kilogram or the kilometer. So that's a good unit to use. Everybody understands it. And now almost everybody understands kilo, mega, giga, 1,000, million, billion. That's all easy. And when you present in the metric system, we all get this. But the US started trying to move over to metric back when I was in middle school, back around 1970 something. And DOD went to hard metric back when I was working as an aircraft contractor back in the 1980s, 1990s. Every U.S. aircraft built in this time must be built in hard metric, not a single SAE unit in the mix. But the Energy Department and the EIA is still locked in the past, and we have pounds, mass, slugs, G-pounds, horsepower, therm, barrel, gallon, watt, kilowatt hour, trillion kilo, billion mega, million giga, 1,000 million kilo. Yes, I understand the authors need to put these in perspective. 1,000 million kilowatt hours gives you a better idea of just how big these things are. Don't put them in the graphs and tables. Use standard units in the tables. Otherwise, we are the high priests of science. Hilary Sillitoe, co-author of Scotland 2070, in a video he put out a few months ago, compared carbon offsets to church indulgences, where rich people could pay the Catholic Church large donations to the church in order to have their sins forgiven. That was an indulgence. And I agree with Professor Sillitoe. I have the same opinion. But I compare modern scientific jargon to church Latin and chaining the Bible to the pulpit. Just plain folks can't tell if we're telling the truth if they can't understand what we say. And we are living in a time where everything we do is in doubt. And anyone who's trying to determine the truth has to slog through these reports and determine, did the person who did this report get it right? Now, I got my previous video wrong, and that's why I'm dwelling on this. But part of why I got it wrong was I got bamboozled by this confusing EIA chart. EIA Must Use ISO. The USA is the largest energy consumer. A fundamental tenet of democracy is disclosure. Obfuscation defies disclosure. We cannot be informed voters and make informed decisions on any of these policies if we can't go back individually with a high school education and determine, are the data being presented, is it valid? Do the units add up? Can we even understand the units? So if you want to do one thing this year to really help move the U.S. energy effort forward, call your congressman and pressure them to tell EIA all presentations, power in watts and energy in watt hours. You can throw whatever kilo, giga, mega on it you want to get the units smaller. We can deal with that, but let's standardize the units. I have lost more hours on EIA units and world units than I have on the entire physics of everything I'm showing you in these videos. Deep breath and move on. If what we've shown on the oil rigs are not enough, we can make them larger, we can anchor them more solidly, but the rigs are anchored to the seafloor down to 3,000 meters. OroAzul units don't need the rigs, they just need the anchors. And thanks to the drilling industry, we now know how to make tethers and anchors. We can do them out of Spectra, the rope that floats, in which case, since it's neutrally buoyant, the entire cable is free floating and has no load on the float. That was examined for the oil industry years ago. I don't think it worked well for them, but it could work very well for us. So we can do all this stuff. Now, through all the videos preceding here, especially in that complicated one on the hydrogen compression, we left out, what do we do with the O2? We're cracking all this hydrogen. We see this NASA video, an excerpt of it, on ocean currents. we can see that right here on the U.S. coast off Florida down to the Caribbean Sea and inside the Gulf of Mexico, we have regular whorls and eddies running in the speed ranges I'm discussing. The Gulf Stream has been clocked at running 5 knots. I targeted 4 knots. We have currents in these areas regularly running in the 3 to 4 knot range, and we can anchor at those locations. So we went through how to crack the hydrogen, how to put this stuff down. What happens to the oxygen? Well, we can strip it with the hydrogen and use it for cogeneration and then getting ideal mix when we go to burn the hydrogen. But right now, the Gulf of Mexico has a huge problem with oxygen starvation due to phosphate overload leading to dead zones. And a lot of these oil rigs are near the dead zones. So if we start cracking the hydrogen down below the oil rigs, and if you go back to one of the earlier slides, some of those oil rigs are going down more than a kilometer already, which gets us down into the liquid oxygen compression zone. Then we can start dumping the oxygen as it cools off once it's warmer to cool the water out here and reoxygenate the dead zones. Now, there's a possibility that oxygenation may actually also lead to deacidification, but I'm not an oceanic chemist. I'm going to leave that up to them. What we do know is that we can dump massive amounts of oxygen back into the dead zones. All right. When I say massive, we're talking about powering a planet. So we're talking amount of oxygen from this process enough to power a planet. Sometimes I refer to this as inverse terraforming, what I like to call terra reforming. So we can use the supercooled air and we can cool the ocean to some extent. Whether it's significant, I'm going to leave that up to the climatologists, but we are definitely dumping a whole lot of cold into the overheated ocean and drawing energy out of it. So we saw the oil rigs are big. We're talking about the cracking. We're talking about the petroleum chemistry, whatever. And we saw from the Saudi Arabian example that you can put entire theme parks on these oil rigs. So derelict oil rigs as refineries. If we can suck the carbon back out of the atmosphere during the heat exchanging process, then these are already small cities and they're already able to ship petroleum off these rigs because, well, that's what rigs do. They ship the petroleum. So if we can start using these as the foundations to use this cheap energy to start forming the synthetic petroleum, that gets us into the bridge fuels. And bridge fuels, even if we go all electric, unless we want to lose the ability to fly from New York to Tokyo in 15 hours, the aviation industry is going to need bridge fuels for at least 50 years to come. So in this case, let's make those fuels by sucking the carbon out of the atmosphere as a side effect of our process, and then doing the conversion to petroleum on the abandoned rigs, and let the rigs continue shipping petroleum back to shore, but synthetic petroleum sucked out of the atmosphere. Okay, so what Dark Sky is seeking? We are struggling to build minimum size demonstration units funded by our founder, me, and small donations. Some of them are $1,000 donations, but compared to saving a planet, these are really pretty tiny donations from a few true believers who have seen what we're doing and understand why we're doing it. We are seeking roughly $1 million in initial R&D funding to produce, test, and document technology demonstrators out at our Bantayan research site. Okay, why did I say roughly 1 million? Well, one of the things I have found through briefing people on this is there is a wide variation in what different people consider adequate proof. We've spoken with engineers who regard hanging a collector off a bridge as adequate. Hey, you hang this thing off a collector and see the thing, I know this thing works. We're ready to go. But I'm talking to speculators who demand 8 months of at-sea operations with videos and showing all the power coming off. They totally ignore that if we're doing 8 months of at-sea operations, we got to put the power somewhere. What are we going to do, boil the water off the boat? We'd have to set up the entire process to get those 8 months of demonstrations, but that's what they require for adequate proof of that we can do this. Then we get to the academicians in universities who require volumes of academic studies, laboratory testing, and numerous articles in the trade journals. Each trade journal sets you back about 6 months and about $3,000 to pay the vanity press, we now call scientific trade journals, to pay them to publish your articles so other people can read it. Since we're self-funded and don't have a funder, I didn't feel like forking out $3,000 to get an article published. Each has a different cost, leaving the choice to the funder. So 1 million will allow us to perform minimum proof of concept testing, get a couple of things operating on a boat, build some real production circuit boards, get us out there, get some power off it, get some batteries, bring it back into shore, show it powering some homes and e-bikes. 1 million minimum to do that within the next 12 months. And this is engineering estimates. Things will go wrong. So how will your donation be used? Our research has shown that no publicly traded company is able to assure sustainable and ethical use of this technology. The father of green investing, Tariq Fancy, has actually come out publicly and says the entire concept of green investing cannot work, and he's left the investing business even though he started the whole concept. Because as soon as there's a bad quarter and the stock price is about to tank, every bit of ethics and morality and goal that the company set up will be thrown to the curb so we can make the quarterly report. Only a nonprofit NGO with an environmental mandate can assure this technology and its revenue is used properly to heal our planet and achieve sustainability. If we are successful, you will be aiding us in creating a self-funded environmental NGO owning the most profitable energy sources in history. Well, it's nonprofit, so it can't really be profitable, but all the money that would normally go into profit comes into the NGO, and then it redonates it back out. So imagine World Wildlife Fund, Greenpeace, Sierra Club, the Cousteau Society, Mission Blue, all those folks out there sharing ownership in the revenue stream that replaced fossil fuels. Whatever replaces fossil fuels will be tapping into a revenue stream as big or bigger than what they have now. And all of that revenue will be pouring through this NGO which we're forming, and you can be a part of helping to form that. Okay, as you can see, when I get into this, I can get really quite emphatic about this because I think, and a lot of people have been reviewing this, think we are on to the long-awaited answer of answers, the way in which we can actually turn humanity and the biosphere's course away from imminent mass extinction and back towards sustainability. Thank you for listening to the Deep Ocean Energy portion of the OroAzul project from Dark Sky Innovative Solutions. I'm Bob Tipton, and for more information, please reach out and contact us at info@darkskyinnovation.com. Please enjoy your morning, afternoon, or evening, whatever the case may be in your time zone. And thank you for watching.